തുടങ്ങൂ സാർ, തുടങ്ങിക്കോ സാർ, സംസാരിച്ചോ.
Good afternoon. I think I'm audible to all of you, right?
Hello.
Yes. Okay. Hello. I would like to welcome all of you to the Silver Jubilee lecture series organized by the Department of International School of Photonics, Cochin University of Science and Technology, CUSAT, in connection with celebrating the completion of 25 years of meritorious service in human resource development in the field of photonics. We are extremely happy and fortunate to have with us today Professor Michel Rerat from Department of Chemistry, University of Pau, France, to give the third talk of the series. With more than 160 research publications in the field of physical chemistry, his expertise in other fields include nanomaterials, density functional theory, materials chemistry, computational chemistry, spectroscopy, and electronic structure. Professor Michel is currently working on a project ab initio calculation of response properties of periodic systems and implementation of the frequency dependent methods in the crystal code. In fact, he is one of the main developers of the crystal code. I'm sure that today's lecture by Professor Michel on the topic refractive index of materials and nonlinear optical effects will be very much beneficial to our photonics community. On behalf of all of us at International School of Photonics, we welcome you and invite you to give the talk.
Thank you. So I can start. Okay, thank you very much for your invitation to present you a part of my work in Pau, at the University of Pau. So I am Michel Rerat, a professor at the University of Pau. You can see it's in the southwest of France, and you can see the Pyrenees, the mountains here, and over there it's Spain. And the logo of the city is two cows like this, and the letters H is Henri, is for Henri IV, Henri IV, who was king of France, was born in Pau, in fact, in 16th century. Here you have a picture also of the river Po now, P-O, not P-A-U, but P-O in Italy, in Torino. And you can see the mountains, Les Alpes here. And over there, it's Switzerland. On the west part here, it's on the left part is France over there. This is Torino with the La Mole, well-known monument of Torino. Why I show you this picture? It is because I am working with the Crystal group, a group of Torino, who built the crystal code 40 years ago, start to build this code 40 years ago. And this is funny because the logo is Torino, a small bull, and here it was two cows in Pau. And also it is interesting to know that the queen of Savoy and Piedmont, the Piedmont is this region in the north of Italy, where is Torino, was the daughter of Henry IV. So there is a very big link between these two, Pau and Pau, P-A-U and P-O. So now I am going to talk about the refractive index of materials and the nonlinear optical effects. And for that, I have to define what is the dipole moment for a finite system at least. So in fact, the dipole moment is given by this formula, mu letter here. with this term, the first term corresponds to the position of nucleus multiplied by their charge, atomic number. This term is constant if you have a fixed molecule, a fixed geometry, sorry. But here you have the part, the electronic part, which depends of the electron density, and the electron density is the square of psi, the wave function of the Schrödinger equation that we are trying to solve. And if there is an outer electric field E0, external field E0, in that case, the Hamiltonian operator is the well-known one, the kinetic one here, P square over 2m, and the Coulomb potential one, plus now an additional interaction term which corresponds to the Stark effect. So you have H0, the H0 means there is no interaction with field. And this term is the interaction between the dipole moment and the electric field. Obviously, there is another term which is not written here because it is constant, as I told you, if you are interested by a fixed geometry. So it's just, you have just to add a constant for this nuclear term. I will discuss about it later. But I am interested by the electron density. So if there is an electric field, outer electric field, in that case, the dipole moment will depend of this electric field and can be developed as a series, a Taylor series like this. Mu0 is the permanent dipole moment, if exists, of the system, of the molecule. For an atom, it's 0, obviously. And the linear term here in E0 is the coefficient in front of E0 is the polarizability. And beta 0 and gamma 0 are the first and second hyperpolarizability, respectively. And you can go on here, but we will see that it's not necessary to go over gamma term. So we can neglect this term, as we will see. Now, if we're interested by materials, condensed solid, condensed matter, in that case, you have a lot of molecules or atoms, or yes, atoms in a cell, in cells, and then you can have a dipole moment, induced dipole moment. So induced dipole moment is all, it's mu minus mu0. It is all the terms which depends of E0, the amplitude of the field. So if we have these molecules inside between the planes of a capacitor, then you can create you apply the field, and this creates induced dipole moment everywhere. And in that case, there is a dipole moment per unit volume, which is called polarization vector. And in this direction, the same direction as E0. But it creates an opposite field, minus P over epsilon 0, which is screening the applied field, in fact. It means that the macroscopic field, which is measured, is E, is the total field, which is equal to something like an applied field if there was nothing here, but minus P over epsilon 0 due to the fact that there is matter here, responding to the applied field. So epsilon 0 is the electric permittivity, and P over epsilon 0 is like a field in that case. So epsilon 0 is 10 power minus 11 farad per meter, and but it is equal to 1 over 4 pi in atomic unit system, in the atomic unit system. And later we will use this system, this atomic unit system. So you can also develop this polarization vector as here, and but now P over epsilon 0 is a field, and now you see that you have some other letters, chi1, chi2, chi3, corresponding in fact to alpha 0, beta 0, and gamma 0. But now it's per unit volume, so it's a dipole moment divided by a volume. And Chi1, Chi2, Chi3 are called electric susceptibilities. There is, by definition, no factorial term now here, while there was a factorial terms here for the microscopic properties. This is the definition. So an interesting property is the ratio between E0, the applied field, the displacement field, if you prefer, divided by the macroscopic field, which is equal to 1 plus Chi1. So the dielectric constant, we will see it later, is the property of interest in materials. So this is the relative dielectric constant. It's a ratio between two fields, so there is no units. And Chi(n) are Chi2, for example, as units of the inverse of a field, and Chi3, the inverse of a field square. And what is interesting to know is that one atomic units of field correspond to 10 power 11 volt per meter. So it means that if you, I work, for example, with experimentalists using a static electric field on the material, and they could obtain 30 kilovolt per centimeter, which is relatively large, but you see that it is less than 10 power minus 5 in atomic units. And if they increase their field, there are some problem of breakdown field due to phonon. But so you see that if it is 10 power minus 5 atomic units, these nonlinear terms, Chi2, Chi3 multiplied by E square or E cube, will be very small compared to the linear term. So with static electric field, it is very difficult to see nonlinear terms, Chi2 and Chi3. But with laser, we can obtain very large amplitude, field amplitude. For example, in the laser megajoule, that is a big laboratory in the south of Bordeaux, where we are trying to, Europe, I think it's, or maybe the world, I don't know if it's a laboratory of researcher from Europe only, but they are trying to do fusion of hydrogen atom in helium with a very intense laser. And for example, they deposit, we try to deposit a megajoule on a target of 10 millimeter cube. It means that the amplitude of the field is approximately equal to 1 atomic units or even more. Or it means also in energy that you have the wavelength is correspond to 1000 nanometer generally. So the number of photon is approximately equal to 1 mole or even more deposited on the target on 10 millimeter cube during, I think, 1 picosecond approximately to try to start the fusion. Okay, so now, and in that case, obviously, Chi2 and Chi3 now are very important because it will give you a large interaction with laser. So with laser, we can observe the nonlinear effects. So if there is frequency now, the electric field is frequency dependent. So the polarization vector, which is proportional to the electric field by Chi1 at the first order of perturbation, the first term in the Taylor series, in that case, oscillate as the electric fields. Here you have, for example, an electron in its potential, and the field is in blue, is oscillating with a blue frequency here, this amplitude, and then the polarization vector is following exactly this oscillation. If you are in the visible spectrum or UV visible spectrum, in that case, the ions cannot follow that. It is too quick. They are too heavy. So when they want to move in that side, the field has changed this direction. So it cannot move. But the electron is very light, so it can follow exactly the oscillation of the field. But due to the nonlinear terms now, you have, for example, with chi2, you can create a field. The square of this field, even if it's the same field, can create a 2 omega frequency. The product of this field, if they have the same phases, omega and omega with the same sign, so it means that there is a 1 photon of omega interacting with the materials, and another one with the same materials, and then you have a scattering photon of 2 omega. So the energy is conserved, but here you have 1 photon of 2 omega obtained from 2 photons of omega. So this is what we can see oscillating twice more rapidly than the blue one with the green. The green part is the second harmonic generation. It's called the second harmonic generation. So you have created a polarization vector of a field, a response field, which is oscillating twice more rapidly than the electric field of the laser. You can also obtain the annihilation of the frequency, of the phase frequency, and then you create a static field. This is the red part here, and it is called optical rectification. So you have created a static field with a laser, only one laser of frequency omega. And if you mix, and you will see the Pockel's effect, if we mixed an electric field, which the laser field with the frequency omega and the static one, you can create something else. We will see it later. So an interesting spectroscopy, the second harmonic generation spectroscopy, which allows to see molecule at the surface of a crystal, for example. Because in fact, chi2, it depends of chi2, as you can see. Second harmonic generation depends of chi2, this term here, but with minus 2 omega, omega, omega. This chi2 tensor of rank 3, it's a tensor of rank 3. Chi1, or the polarizability, is a tensor, is a matrix, a tensor of rank 2. Chi3 is a tensor of rank 3, and Chi3 is a tensor of rank 4. But this tensor, beta or Chi2, is null when there is an inversion symmetry. So it means that generally Chi2 is 0 for most of crystals. But even if it is null for the bulk, it can appear not null here due to this molecule in an asymmetric environment. Here it's the air and or the vacuum, and here it's the bulk. So this molecule do not see the same, have lost their symmetry environment. So there is a Chi2 value which is due to this molecule, the clouds of the electron clouds of this molecule. So you can see with the second harmonic generation, this molecule, only this one. So it can be an interesting spectroscopy for surface of materials. Here, it's a second harmonic generation imaging of hemoglobin of blood, and there are some parasites of malaria in blue, in fact. They are detected by the color change. In fact, be careful, the colors are faked because you cannot see in the visible spectrum a frequency, and it's triple frequency. So the third harmonic generation, sorry, is like the second harmonic generation, but with 3 fields with the same phases, omega 1, omega 2 and omega 3 equal with the same sign, and then you will create one photon with 3 omega. You need 3 photons of omega, and you create a photon of 3 omega. So now, what about the refractive index? This is the title of my talk. So now I can say that I can speak about it. N, the refractive index, is the square root of epsilon r. In fact, the formula is a little bit more complicated, but for non-magnetic materials, mu r, the permeability, the magnetic permeability, is equal to 1. And C here is the chirality of the material. But generally, materials like tartaric acid or even quartz, alpha quartz, have a chirality. But generally, this value, this term is very small compared to the square root of epsilon, the inverse of the square root of epsilon. So we can neglect these terms also. So at the first order of approximation, we can say that the N, the refractive index, is equal to the square root of epsilon r. So I recall you that epsilon r is the ratio of E0 over E and is equal to 1 plus chi1. It's positive, it's larger than 1. Chi1 is positive for materials in their ground state. For excited states, it's different. It can be negative and the epsilon can be negative. So the refractive index can be complex. Okay, so now look at n. N square minus 1 or n square is epsilon. It's the same, huh? So we can say that. Can be written like this. In fact, it's a Selmayer's equation, the Selmayer's equation, and you can add some other terms, B4, B5, and C4, C5, etc. And this is a formula obtained by Fit. And in fact, B1 corresponds to oscillator strains, and C1, and B1, B2, B3, sorry, correspond to oscillator strains, and C1, C2, C3 correspond to transition energies. So B1 with C1, the coupled B1, BI, CI will give you the UV visible spectrum, in fact. So here we can see that between the infrared part spectrum here over 10,000 centimeters minus nanometer, sorry, 10,000 nanometer. So for large wavelengths, here we have the infrared spectrum, and here this is in gray the visible spectrum, and for smaller wavelengths we are in the UV visible spectrum, in the UV spectrum. And you can see that between the infrared spectrum and the visible spectrum, the refractive index is practically constant, doesn't move. It's for rutile, corundum, calcite, quartz, calcite, fluorite. These are the value of the refractive index for these materials between the infrared and the UV spectrum. But here you can see that it is increasing very quickly. It corresponds to lambda equal to C1, lambda square equal to C1, the first resonance in the UV visible spectrum. So it becomes infinite. And here it should, if I plot at this, if I look at these n values for larger wavelengths, then it will go to minus infinite here, going very, not minus infinite. In fact, be careful. N is not real, it's a complex term, but it's going very low here. And if you pass the infrared spectrum, it means you are going to the static case, which is on the right here, you will have again n value, which is very high compared to here, if the system is ionic, if the material is ionic, and then you will have an infinite value of n here, going to infinite, but up there. And then going down, oscillating because there are resonance in the infrared part, then coming back to a constant here. And now in this part, the ions cannot follow the electric field, the oscillation of the electric field, as I told you before. So you have something which depends only on the electronic contribution of the movement of electrons, of the cloud, electron cloud. And then you have resonance, as I told you, in the UV visible spectrum. You have the spectrum here, the UV visible spectrum here. We will see it later also. Okay, so this is interesting to see when we are far from absorption spectrum in the infrared or UV visible spectrum. It's interesting to see what is called the constringence, the dispersive power of the materials. It is the variation of n with the frequency of the laser or the light. Yeah, it's not the laser compulsory, but light. And then it's a prism, and you can do dispersion of light here. N depends on the wavelengths, as we saw it here just before. You see it is changing here a little bit with the wavelengths. So with the blue wavelengths, small wavelengths, then you have a larger refractive index. And with the red one, you have a smaller. You are going to the large wavelengths. So you have the dispersions of the light, the sunlight, for example, by a prism. A small deviation for the red one and the bigger one for the violet or blue one. Yeah. So the constringence is, in fact, this factor, this ratio between difference of refractive index. One corresponds to the vacuum or the air, and D is the refractive index of the materials for the D wavelengths, which correspond to the sodium, the yellow sodium light here on the spectrum of the sunlight spectrum here. And NF minus NC correspond to the refractive index of the same material, but for F, the blue part, I don't know exactly what is it here on the C line. The C line, maybe it's iron. I don't remember the atoms, the lines to which atom correspond this line, but they correspond to this very accurate wavelengths. So this gives you the dispersion, an idea of the dispersion of your refractive index of the material. And then you have some example like that of the Schott company, which build glasses with different value of n along the y-axis, and on the x-axis it's the constringence. Yeah, so a large one on the constringence on the left part of the diagram here, and the refractive index is large when you go up there. Okay, so in green and the blue and the red are the kind of glasses. In green, it means that there is no lead, no arsenic atoms inside the glass. And in the red one, yes. So you have a lot of different kind of glass with different properties made by made by the Schott company. Okay, but you can also change, as I told you at the beginning of my talk, you can create a dispersion with the amplitude of the field. In fact, if you look at the polarization vector and its Taylor series expansion, then you can obtain, so you have this part chi1 proportional to E cosinus omega t. But if you include also a static field, like in the focal effect, so you have a laser plus a static field, then you can obtain this chi2 process, nonlinear process, with omega and 0, and you obtain a scattering photon of frequency omega with E0 here. So you have a term in E0 multiplied by E omega cosinus omega t. So it means that the refractive index now is equal to N0 omega, as if there was not enough electric field amplitude. It's not large enough, but this term comes from the static field that you add it here. And you can see this phenomenon. So you can tune the N omega, the frequency, the refractive index, with for a given frequency omega, you can tune it with the amplitude of the field, of the static field. And N1 is related to chi2, in fact. But as I told you, often chi2 is equal to 0 per symmetry reason. So in that case, you have you can go at the second nonlinear properties, optical properties, as in the K effect. In that case, you have a refractive index which becomes dependent of the, no, it's not index, sorry, it's intensity dependent refractive index. It's not index here. You have to correct that. Intensity dependent refractive index. It's the well-known Yttria process. And this is what I am working on this effect. So in that case, in this effect, you have just a laser, but you are looking now at the power 3 of the electric field. So E square here and here, E here. So you have still something oscillating with cosinus omega t. So you didn't multiply the frequency by 2 or 3. You have just the same frequency here, but it depends on chi3. So you need two fields with the same phases omega on the same sign, and the other with an opposite sign, and then you will create an oscillating polarization frequency, polarization vector, which has the same oscillation as the laser one. So in that case, N depends of N0 omega, but there's an additional term, N2 omega, which is proportional to chi3, and depends on this term will be seen if the intensity of laser is enough. So you can tune now the refractive index for a given frequency of the laser, the same frequency of the laser, by changing the intensity of the laser. And I will show an example why it can be very interesting to do that. So just a slide to tell you how we can go from microscopic properties, the polarizability, the first and second hyperpolarizability, to the macroscopic ones, chi1, chi2, chi3. We saw that epsilon was the ratio between E0 and E, so equal to 1 plus chi1, and chi1 in fact is equal to 4 pi alpha over V, because P is like a dipole moment, but divided by a volume. It's per unit volume. You need the density of matter, 1 over V. So if alpha is the polarizability of a unit cell in the crystal, V is its volume. So you see that alpha is in Bohr cube in atomic units. It's an abuse of language, because 4 pi is not is equal to 1 over epsilon 0. And as I told you, epsilon 0 has a unit. It's a farad per meter in the system international. So you must be careful that we say that alpha is in Bohr cube, in fact, is like a volume. Obviously, you can understand that if you have a a large atom. What does it mean, a large atom? Because it's not a physical property, a large atom, the dimension of an atom. It's not easy to define the volume of an atom. But the polarizability, yes. And you can see that if you have a large atom, it means that electrons are far from the nuclei. They are very easy to deform, to go far away from the atom. If you have just a charge near or an electric field. So you see that the deformation of the large atom is due to the electrons which are very far from the nuclei, and then from the nucleus, and then you can understand that the polarizability, which explains the deformation of an atom, of the cloud, electron cloud in presence of a field, becomes very large. Okay, so we can see that if you have a large atom, you have a large polarizability. But I will say that alpha is the polarizability that can be measured, but not the volume of an atom. The volume of a cell, yes. So that's why 1/V is well defined on alpha. Then if you want to calculate epsilon, you need to calculate alpha. And chi2 is like beta, or chi3 like gamma, but you have just to divide by the volume. It means just multiply by the density of matter. Okay, so I have to calculate alpha, beta, and gamma as a theoretical chemist, but it's not an easy job. I mean, it's in fact alpha, beta, and gamma are the second, third, or fourth derivative of the cell energy with respect to the field. So their expression in the perturbative is an infinite sum of perturbative terms in the theory of perturbation. But dependence of the discrete terms, discrete states, but also continuum. In fact, if you want to calculate alpha of the polarizability of the hydrogen atom, and you put only, we know very well the expression of the excited states and the continuum, but if you put only the discrete states, then you will have only 80% of the value of alpha, which is equal to 9/2, if we don't take into account the relativist effect. So you see that even if you know all the excited states, the discrete one, then it is not finished. You cannot obtain the good value of alpha. You obtain only 4 instead of 4.5, even less than 4. So you see, even for the hydrogen atom. So imagine for a molecule or for a crystal. So the convergence of these properties is very low with respect to the states, and the number of states put it in the sum of these perturbative terms. And moreover, we have a problem of definition of a dipole moment in solids. What is a dipole moment, for example, of a polymer AB? Is it the dipole moment of AB or BA? Because BA is exactly the same as AB. If it is infinite, periodic. So if you want to define dipole moment, you must know the edge, the surface. But in our calculation, we can get rid of this dipole moment if we are interested only by the derivative of this dipole moment with respect to the field. It means the polarizability, the beta and gamma hyperpolarizability. But in that case, the operator, it's very strange and very interesting problem, physics, very interesting, or maths. In fact, the operator, position operator R is no more Hermitian in the CO basis set, in the crystalline orbital basis set, which where the von Karman condition is respected. Von Karman condition means that let's say the last atoms of the polymer on the right correspond to the left, the first one on the left. You do a circle, in fact. but in 3 dimensions for crystal. So this makes the Hamiltonian block diagonal, and the operator now must be replaced by that one in that case, which is a bit strange because you have an operator acting at the key point of the reciprocal space. So it's very tricky, yeah, but interesting because you can have now, if you, the formula are very more complicated, but if it is programmed, now it's very easy to calculate alpha analytically with a method like the self-consistent coupled pattern method, which is very used for molecule, coupled perturbative method or Consham method. You have heard about this method, and can obtain this sum, this difficulty, overcome this difficulty of sum over all the true excited state. You don't need to know all the true excited state, the spectral states. The ground state is enough, and you can use the virtual orbitals to obtain a relatively accurate polarizability or hyperpolarizability, and then dielectric constant and Chi2 and Chi3 properties. So all this kind of thing is included in the crystal code. Now I have an application here. I don't know how many times I have again. It's Yttria Stabilized Zirconia. It's a contract that I obtained with colleagues, experimentalists, and the idea is to realize multi-wavelength sources based on a simple pump laser with only one laser with a frequency omega. We want to change the refractive index, as I told you here, with N2 here. So we need to calculate Chi3. The idea is that in fact, we need to have a very large value of Chi3. And we could use the silicon, which give something maybe 10 times or even more larger than the Chi3 of zirconia, ZRO2. But in the case of silicon, you have 2 photon absorption coming from these terms, like the second harmonic generation, in fact. You have something where the 2 photons of omega can be absorbed and without diffusing a photon with 2 omega, but just absorbed by these 2 photons. In that case, the intensity of the laser will decrease a lot. So in that case, this value N2 E square, N2 is maybe with zirconia much less than for silicon, but E square remains E square. With silicon, this E square will decrease a lot due to the photon absorbed. E square means the number of photons. But if many of these photons disappear because of the 2 photon absorption, in that case, you decrease this. And then this product, N2 by E square, is not so large. So that's why my colleague from experiment try to use zirconia, which has a good Chi3 value, not much less than for silicon, as I told you. But there is the gap, the distance between the occupied orbital and virtual orbitals, or excited state, let's say the first transition energy is around 5 or 6 electron volts, and is much more than twice the value of the photon laser, which is generally equal to 0.8 electron volt, corresponding to a wavelength of 1.5 micrometer. And this wavelength is used in the optical guides, that is used in our everyday lives, everyday's life. Okay, so generally the wavelength used is 1.5 nanometer, corresponding to 0.8 electron volt. So the double of 0.8 electron volt is only 1.6 electron volt. It's less than 2 electron volt. And in that case, you cannot obtain 2 photon absorption. So the laser intensity remains. And so, as I told you, for zirconia, you have a gap of 5 or 6 electron volts. So you have no 2 photon absorption problem. But generally, the system must be a cubic system to be laid on a sapphire or silicon to build the guide of light. But zirconia, Princeton zirconia is not stable in the cubic phases. So that's why we need to put yttrium inside to stabilize the cubic phases of zirconia. But in that case, the value of epsilon here or chi3 are decreasing. But fortunately, a small percentage of yttrium is enough to stabilize zirconia. And then you can see that here on the x-axis, it means that we have a small value of the percentage of Y atom, the Y atom. So in that case, it decreases a little bit, but not very much. So it's not a problem to do that. So chi3 is a little bit less, but zirconia is stabilized. So we have to try eventually if there is other atom which can stabilize zirconia. We tried the erbium on the YSZ on Yttria Stabilized Zirconia. We add also erbium, which is a rare earth atom. And in that case, we obtain this density of states picture. But now we have an open shell system. Means that you have not the same number of spin alpha electron and spin beta ones. So in brown here, it's for beta, blue for alpha, and you see that we create the distance between blue and blue here, the occupied orbitals here, and the virtual ones here. It is the gap here, around 6 electron volt. But for spin beta electron, we can see that appears a peak here due to the erbium here. Down, it's the projected density of states on erbium. So you have a little peak due to erbium in the virtual band, in the conduction band. Okay, and then you can increase chi3 because chi3 depends on transition energy, which are on the denominator of of these perturbative terms, in fact. So when you have a small gap, you have a big response property. And if the gap is smaller, then you have a very large chi3. So with erbium, chi3 becomes much larger than for YSZ. But the problem is now it is at 2 electron volt approximately. So we are not so far from the 2 photon absorption if we use the wavelengths of the laser equal to 1.5 micrometer. So the problem is we have to know to choose, we have a competition between avoiding two photo absorption and increasing chi3. So we must tune the percentage of erbium because it's a small peak. So it is as if it was a small step for the response property. If it is a small step, the absorption won't be very strong. But it is a little bit larger than 2 electron volts. So 2 photo absorption should be very small for this system. And chi3 is much larger, is twice larger than for the price time ZrO2. So it can be interesting for that. So I just have to finish that. I show you that with the refractive index or the dielectric constant, is the same. You have a complex part which appears when you are in the absorption spectrum. It's the UV visible absorption spectrum. And the imaginary part of epsilon, or the dielectric constant, or the refractive index, gives you the intensity of the spectrum. So this peak at 2 or 3 electron volt correspond to erbium, is due to erbium. So you can have a 2 photo absorption, but you have to divide the 2.5, 3 divided by 2 in electron volts. So it will be less than, larger than 1 electron volt. So larger than 2 times the photon corresponding to the wavelength 1.5 micrometer. So it should be okay. It should not be a problem to use erbium in the YSZ for this. Okay, I have finished with that, and I thank you for your attention.
Hello, sir. Thank you very much for a very detailed talk. A lot of theory has been explained. So I have a couple of questions. Okay.
Yeah.
So the first question is, how can the hyperpolarizability is estimated for samples in solution?
Estimated, you mean?
Yes.
That's
how do you estimate?
You have a material and you want to estimate it, right?
Yes. Suppose that the material is in solution. So how do you replicate
in
that?
solution.
Exactly.
So yeah. So in solution means that there is 2 things in chi3 and chi2. I don't know if you are talking about chi3 particularly, but yes, you have two things. You need to have if you want a large value of chi3, you need then a large value of gamma, the second hyperpolarizability, the microscopic property. But also you must have a density of matter, important density of matter. So chi3, as I told you, is something like gamma over V. Gamma, the hyperpolarizability of a unit cell, or for example, in solution of a molecule, and the concentration, how many molecules I have per unit volume. Okay, so you need to calculate gamma over V. So let's say it's easy to know if it's concentrate or not. But now if you want to have an idea of the value of gamma, it's not so easy, but you can say that in gamma you have something like a numerator of it's a quotient of a numerator, a ratio between a numerator and denominator. On the denominator, it's a transition energy power 3. So if the distance in energy between the conduction band and the valence band is small, you will have certainly a very large gamma value. But you have a numerator also. And this numerator depends of transition moments now. You have to, but transition moment between the ground state and the excited states, between the valence band and conduction band. Okay, let's suppose in the DOS here. between this DOS at the top of the valence band. Here it's principally oxygen atoms, to the bottom of the conduction band. Here you have this due to the erbium. This distance, if it is small, it means that gamma will be very large. It's proportional to 1 over this distance at the cube value of this distance in energy, the gap value cube.
Okay.
But obviously you need to have a DOS if you have nothing, or if the transitions are not allowed, or symmetry or whatever. In that case, the numerator will be small. So you will have a numerator which is small divided by a gap which is maybe small, power 3, but maybe it won't be very so large. And in gamma, you have several terms also, positive and negative terms. So
also when you have the sample in solution, probably your relative dielectric constant will change, no?
You will have, sorry, I didn't understand your last.
So when your sample is in a solution, probably your relative dielectric constant is different, no? In that case.
Yeah.
Yeah. So you don't have
yes,
to.
Yes. Yeah. No. Yeah. In fact, no. Here it's for one cell. I mean, for one molecule. This
okay.
DOS. Now, if you have a lot of molecules or not, it's the volume V, which is important. So it's independent. This DOS, density of states, is independent of the number of molecules.
Okay,
or the number of cells, or if the density of matter is small or large. But obviously, if you have no molecules, if you have one molecule among in the vacuum, sometimes obviously the response will be small, but not due to this problem of DOS. So there is different problems. Density of matter, the volume, the 1 over V, the number of molecules in solution, the concentration is due to the concentration. But I was talking about gamma, the microscopic property, which depends on the DOS of one cell, of one molecule.
Okay.
And then it depends a lot of the gap. But not only you have for gamma, for alpha, it's much easier because the term is much easier. You have oscillator strengths, which depends on the transition moment between the occupied to virtual orbitals. And these are the transition moment. The oscillator strength is the 8 here. And divide by so alpha is like this peak, the 8 here, divide by the square of this distance in energy. This will give you the contribution of this peak. Obviously, you have to do a sum over all this peak surface, but divide weighted, let's say, by the transition energy square. So
maybe in connection.
Yeah.
Maybe in connection to this question. So what if you have a heavy metal? Do we have to take into account the relativistic effects?
Lattice effect, you mean?
The relativistic effect, yeah.
What do you mean by lattice effect?
No, the relativistic effect for the heavy elements, the relativistic effect.
Je comprends pas. I don't understand lattice. What is lattice?
The relativistic effect, relativistic.
Relativist effect. Sorry, excuse me.
Yeah.
Yes. So you are right. With erbium, probably there are relativist effect, important relativist effect on the energy due to the spin-orbit coupling.
Yes.
But I don't know. For the moment, I don't know. Probably this will change. This
the position of the states.
You are totally right. This can be very important, but unfortunately, for the moment, we haven't this in the crystal code, and I don't know other codes doing that for calculating gamma, as I do it for a periodic system crystal. But it is, you are right, it's very important to, it will be very nice to obtain that. So I know that the colleagues of Torino, of the crystal code group, in the crystal code group are doing that. I think they have already the spin orbit effects on the, for molecule, for finite system. I don't know about periodic system, but I would be very interesting to do that. So it is an objective that I have with normally a student of Torino, which is a Canadian guy, in fact, who passed his thesis in Torino, and who should come here from January, this January, but with the problem of COVID, stuck up there, and we cannot go on. And he is doing the spin orbit, including the spin orbit effect in the relativist effect in the crystal code. But I don't know where he is. No. Sorry?
Okay. So we do not have any other questions, and if not, thank you very much for accepting our invitation and for giving a wonderful talk. Very, very informative talk.
Thank you to you. Thank you.
Yeah. Thank you very much, sir. Thank you. Thank you.
Okay.
See you later.
See you later.
Thank you very much. Yeah.
Ciao, ciao.